The de Havilland Mosquito shouldn't have worked. By every measure of conventional military thinking, in 1938, Geoffrey de Havilland's proposal was absurd. A bomber built almost entirely from wood, carrying no defensive armament, relying solely on speed to survive. The Air Ministry's response was predictable. Polite rejection. Metal was the future, would belong to the Great War, to buy planes and canvas, not to an air force preparing for mechanized conflict against the Third Reich. Yet de Havilland persisted, and within that persistence lay the seed of one of the war's most elegant aircraft, and the stage for an unlikely hero who would make it faster. Still, Britain in the late 1930s faced a grim arithmetic problem. Rearmament was accelerating, but aluminium was scarce, rationed, fought over by every branch demanding fighters and bombers. De Havilland's genius was recognizing what others saw as limitation. The company had spent decades perfecting laminated wood construction, bonding birch plywood with Ecuadorian balsa and Canadian spruce using cast-iron glues developed for furniture. These techniques produced structures light, strong, and crucially buildable by furniture makers and piano factories, skilled tradesmen locked out of metal airframe work. The Mosquito would be a war machine assembled by peacetime craftsmen, a bomber that didn't steal resources from Spitfire production. The design that emerged in 1939 was audacious. 2 Rolls-Royce Merlin engines, the same power plants propelling Hurricanes and Spitfires, mounted on a sleek fuselage with a wingspan of 16.5 m. No gun turrets, no bomb aimer's compartment, just pilot and navigator in a cramped cockpit betting their lives on mathematics. The performance estimates promised something extraordinary. A top speed exceeding 400 miles per hour at altitude, faster than any fighter then in service. Speed as armor, speed as weapon. The first prototype, painted training yellow, lifted off from Hatfield Aerodrome on November 25, 1940. Test pilot Geoffrey de Havilland Jr. pushed the throttles forward, and the Mosquito did something unexpected. It felt eager. By February 1941, official trials at Bosom Down confirmed the figures weren't fantasy. At 22,000 feet, the aircraft touched 392 miles per hour, and this was a prototype. Heavy with test equipment, engines not yet optimized. The Air Ministry's skepticism began to crack. But speed on paper and speed in combat are different creatures. The Merlin XX engines fitted to early production. Mosquitoes were rated for specific boost pressures. 14 pounds per square inch for takeoff, less for sustained cruise. These limits weren't arbitrary. Rolls-Royce engineers had calculated detonation margins bearing temperatures, piston crown stresses. Exceed those figures, and you risked catastrophic failure. Shattered connecting rods, melted pistons, engines tearing themselves apart at 20,000 foot over enemy territory. The manuals were explicit. The limits were sacred. Yet by late 1942, as Mosquitoes began flying deep penetration raids into Germany, crews were reporting something troubling. They were fast, yes, but not quite fast enough. The Luftwaffe's Focke-Wulf 1-90 and the latest Messerschmitt 109G variants were closing the gap. Interceptions were becoming uncomfortably frequent. A Mosquito bounced over the Ruhr might outrun its pursuer, but the margin was thinning. Pilots began returning with stories of tracer rounds passing closer, of dives that barely opened the distance, of engines screaming at emergency power that still wasn't quite emergency enough. The Mosquito had proven de Havilland's vision, but now it needed something more, something the design office hadn't anticipated and the manuals didn't permit. It needed someone willing to read between the lines of engineering tolerances to see not limits, but possibilities. It needed someone who understood that rules written in peacetime might not survive contact with war's demands. Roderick Banks wasn't supposed to change anything. He was a fitter, not an engineer, a distinction the Royal Air Force hierarchy took seriously in 1942. His workshop at RAF Maham in Norfolk was one of dozens scattered across Bomber Command, maintaining the Merlin engines that powered Lancasters, Halifaxes, and the growing Mosquito fleet. His job was execution, not innovation. Strip the engine, inspect the components, replace what's worn, reassemble to specification, sign the logbook, send it back to the line. The system worked because men like Banks followed instructions precisely. Except Banks had a peculiar habit. He read everything. Not just the maintenance manuals, but the engineering specifications Rolls-Royce included with engine deliveries. Documents most fitters ignored, dense with thermodynamic calculations and metallurgical tables. Banks studied them during meal breaks, tracing the logic behind boost limits and fuel mixture ratios. He joined Rolls-Royce's Derby factory as an apprentice in 1935, spending 4 years watching Merlin development before the RAF recruited him. He understood these engines at a level unusual for someone wearing a sergeant's stripes. What Banks noticed in early 1943 was a discrepancy. The Merlin manual specified maximum boost pressures, but the engineering data showed the components could theoretically withstand more. Not much more, but enough to matter. The limit wasn't about what the metal could survive. It was about what Rolls-Royce could guarantee across thousands of engines in varying conditions. A safety margin. Banks began wondering what would happen if you deliberately ate into that margin. Just a little on engines you knew were in perfect condition. The mathematics were seductive. The Merlin's power output related directly to manifold pressure, the boost forcing air and fuel into the cylinders. Increase boost by 2 pounds per square inch, and you gained roughly 100 horsepower. On a Mosquito, that translated to perhaps 15 additional miles per hour at altitude. The difference between a successful evasion and a very short combat career. But there was complexity beneath the simple numbers. Push too much boost through an engine and detonation becomes inevitable. The fuel-air mixture exploding prematurely, hammering pistons with shock waves that can crack metal in seconds. The Merlin used 100-octane fuel, which resisted detonation better than lower grades, but it wasn't infinite protection. Banks realized the margin depended on precise fuel mixture control. Run too lean, too much air, not enough fuel, and cylinder temperatures soared. Run too rich, and you wasted the advantage. The sweet spot was narrow, and it varied with altitude and throttle position. Banks started small. A single engine scheduled for overhaul became his laboratory. He adjusted the boost control unit, a seemingly minor recalibration, advancing the overboost cut by 2. Then he enriched the fuel mixture slightly at high power settings, adding cooling through evaporation. On the test stand, the engine howled at pressures Rolls-Royce manuals classified as emergency only, sustained for minutes rather than seconds. Temperatures climbed, but stayed within tolerance. Nothing shattered. Nothing melted. The evidence was one thing. Convincing anyone to fit it to an operational aircraft was entirely different. RAF engineering officers lived in terror of unauthorized modifications. Every change required approval through channels that moved at bureaucratic speed. Committees reviewing committees' risk assessments filed in triplicate. Banks's modification existed in a gray area, not quite illegal, but absolutely unsanctioned. He needed an advocate, someone willing to gamble reputation on a fitter's intuition. He found one in squadron leader Peter Channer, a Mosquito pilot who'd survived 3 tours and accumulated a healthy disrespect for official caution. Channer had flown the sortie over Cologne in February 1943 when a 109G had nearly caught him during the egress close enough to see the German pilot's oxygen mask. The memory made him receptive when Banks explained what he'd discovered. Channer's response was pragmatic. If it works, it's not illegal. It's initiative. If it fails, Banks would carry the blame. They chose a Friday evening when the station engineering officer was away. Banks and 2 trusted riggers worked through the night modifying the boost controls and fuel system on Channer's assigned Mosquito, serial number DZ414. By dawn, the aircraft sat on the dispersal, looking identical to every other Mosquito on the squadron. Only the log book betrayed the truth, and Banks's entry was deliberately vague. Fuel mixture optimization, routine adjustment. The Merlin engine's boost control system was simpler than most people imagined, which made Banks's modifications both possible and dangerous. At the heart's at a barometric capsule, essentially a sealed metal bellows sensitive to atmospheric pressure. As the aircraft climbed and air pressure dropped, the capsule expanded, mechanically adjusting the throttle's maximum boost to prevent overstressing the engine. In thin air, Rolls-Royce had calibrated these capsules conservatively, building in margins that assumed pilots might abuse the throttles during combat stress, that fuel quality might vary between batches, that maintenance might be imperfect. Banks's first intervention targeted that calibration. Inside the boost control unit, a spring determined how much pressure the capsule allowed before cutting power. By carefully selecting a slightly softer spring, not dramatically different, just fractionally more permissive, he shifted the maximum boost from 18 per square into 20.2. Doesn't sound like revolution, but at 20,000 feet, it meant the difference between 380 and 395 miles per hour. In pursuit geometry, that gap could stretch from gun range to safety in under 3 minutes. The fuel mixture adjustment was more delicate. The Merlin's carburetor metered fuel through a series of jets, tiny brass orifices drilled to precise diameters. Altitude and throttle position determined which jets supplied the mixture, and Rolls-Royce had sized them to run slightly lean under high power. Prioritizing fuel economy and reducing the risk of fouling spark plugs with excess carbon. Banks recognized this compromised cooling. When you're extracting maximum power, the extra fuel doesn't just burn, it evaporates inside the cylinder, absorbing heat that would otherwise stress the aluminum pistons. He addressed this by replacing the main jet with one a single drill size larger, increasing fuel flow by approximately 8% at full throttle. Not enough to flood the engine or waste significant fuel, but sufficient to drop exhaust gas temperatures by 40 degrees Celsius. That margin was survival, detonation, pre-ignition that destroyed engines occurred when cylinder temperatures exceeded specific thresholds. Banks was buying thermal insurance. The Magneto timing received attention, too. The Merlin fired its spark plugs before the piston reached the top of its compression stroke, giving the flame time to propagate through the fuel-air mixture. Rolls-Royce specified 15 degrees before top dead center, a compromise between power and safety. Advancing the timing to 18 degrees extracted more energy from each combustion event, but increased the mechanical stress on the connecting rods and crankshaft. Banks judged the Merlin's bottom end. The crankcase and bearings could handle it, provided the engine was in perfect condition. Worn bearings or slightly oval cylinders would fail catastrophically under the additional loading. This was why Banks selected which engines received modification with obsessive care. Any power plant showing even marginal wear went back to standard specification. Only Merlin fresh from overhaul with new pistons, bearings checked to within 1/1000th of an inch and compressions readings identical across all 12 cylinders received the treatment. He was pushing boundaries, not ignoring physics. The modifications broke no specific regulation because no regulation anticipated them. RAF maintenance doctrine assumed fitters followed manufacturer specifications exactly. The rule book didn't say thou shalt not adjust boost controls. It simply didn't conceive that anyone would try. Banks operated in the silence between explicit permission and explicit prohibition. That gray space where initiative lives alongside career-ending mistakes. Rolls-Royce's official position, had they known, would have been unambiguous horror. Their warranty explicitly voided if operating limits were exceeded. The company had tested engines to destruction, determining those limits, recording exactly when pistons melted, when bearings seized, when crankshafts twisted. The margins existed because catastrophic failure at altitude meant dead air crew, and dead air crew meant liability, investigations, reputations destroyed. But Rolls-Royce wasn't flying combat sorties over the RU, with Focke-Wulf fighters queuing for firing solutions. Banks was betting that brief periods at elevated boost, minutes, not hours, wouldn't trigger the failure modes Rolls-Royce feared. He was also betting on the 100-octane fuel's detonation resistance on his own ability to select only the finest engines on riggers who'd monitor temperatures obsessively during flight tests. The morning after Banks modified DZ-414, Peter Channer took the Mosquito up alone. Standard test flight profile climb to 15,000 feet level flight at cruise power. Then the moment of truth. Channer advanced the throttles to the stops and watched the boost gauges climb past the red line, needles settling at 20. The Merlin's note deepened, a harder, more urgent howl. The airspeed indicator unwound past numbers Channer had never seen in level flight. The proof arrived over Gelsenkirchen on 19th of April, 1943. Squadron leader Channer's crew had been tasked with a daylight reconnaissance run. Photographs of synthetic oil plants in the Ruhr Valley, the sort of mission that invited attention from every Luftwaffe controller within radar range. The Mosquito crossed the Dutch coast at 24,000 feet, cameras warm. Channer's navigator calling out landmarks through the intercom. Clear skies, perfect visibility, terrible conditions for staying unnoticed. The German fighters appeared 18 minutes into enemy airspace. Two Focke-Wulf, one Nint A5S, climbing hard from an airfield near Muster. Their BMW radial engines clawing for altitude. The controller's vectors were good. They'd positioned ahead of the Mosquito's track, cutting off the escape route back to the North Sea. Channer spotted them at 6 miles, two dark specks against cumulus, turning to intercept. Standard Luftwaffe doctrine, close from above and behind, used the speed advantage from the dive, converging fire from 20mm cannons and 13mm machine guns. Channer didn't panic. He completed the camera run, letting the photographic equipment capture its images whilst the FW-190S ate the distance between them. Then he spoke quietly to his navigator. "Let's see what Banks gave us." The throttles were already at maximum, but now Channer activated the override, pushing them past the stops into territory Rolls-Royce manuals marked as emergency only. The boost gauges surged to 20 pounds, then fractionally beyond. The Merlin responded with a snarl that vibrated through the airframe. The Mosquito accelerated like it had been kicked. Channer felt the increase viscerally, not the gentle building of conventional speed, but something more immediate. The airspeed indicator swept past 400 miles per hour, still climbing. The altimeter began unwinding despite the throttles being wide open. They were trading height for speed in a shallow descent that maintained energy whilst opening the gap. The lead FW-190 pilot recognized what was happening and adjusted, pushing his own aircraft into a steeper dive to maintain pursuit geometry. For 30 seconds, he held position, perhaps even closed slightly. Then the gap began stretching. 500 yards became 600, 700. The Focke-Wulf was fast in a dive capable of nearly 430 miles per hour straight down, but it couldn't sustain that speed in level flight. The Mosquito could. Channer watched the fighters fall behind, their pilots no doubt advancing their own throttles to the firewall, extracting everything BMW's engineers had designed into those radials. It wasn't enough. At 800 yards outside effective gun range, the FW-190S broke off. Channer maintained full power for another 3 minutes, crossing back into friendly airspace over the shelter estuary before finally easing the throttles back. The Merlin settled into cruise, temperatures elevated, but within acceptable limits. Both engines had survived. More importantly, so had he. The intelligence officer who debriefed Channer noted the encounter clinically. Successfully evaded 2 FW-190S through speed advantage. What the report didn't capture was the significance. This wasn't a lucky escape or clever maneuvering. It was physics winning. The Luftwaffe's premier fighter, specifically designed to catch Allied bombers, had been outrun in level flight by an aircraft it should have murdered. Word spread through the Mosquito squadrons with the speed that only genuinely useful information achieves. Other pilots began asking Channer questions, and Channer directed them towards Banks with a knowing look. By May, 3 more Mosquitos at Maham had received the modifications. By June, Banks was spending evenings working on engines from other squadrons, his workshop becoming an unofficial performance center. The modifications remained technically unsanctioned, but they were increasingly tolerated by station commanders who cared more about returning crews than regulatory perfection. The combat reports accumulated through summer 1943. On 17th of June, a modified Mosquito outran 3 Messerschmitt 109 G6s over Hamburg. On July 3rd, another escaped a determined pursuit by Kurt Bulligan's aircraft. Bowen being an ace with 112 victories who knew precisely how to prosecute an interception. He couldn't catch the Mosquito. On August 22nd, a crew limping home on one engine after flak damage used Banks's modifications on the remaining Merlin to stay ahead of 2 109s that should have finished them easily. The statistics became undeniable. Mosquitos with modified engines were returning from sorties that conventional aircraft didn't survive. The loss rate for Banks' modified machines ran at less than half that of standard Mosquitos flying comparable missions. Survival bought time. Time bought experience. Experience bought better bombing results. The circle was virtuous. Operation Jericho demanded precision that bordered on suicide. The Amy prison in northern France held 120 members of the French resistance scheduled for execution by the Gestapo on 19th of February, 1944. London had received desperate messages through SOE networks. Break the walls, give them a chance to scatter, or they die. The mission required Mosquitos to strike a 3-story building with 500-pound bombs, breaching specific walls without collapsing the entire structure onto the prisoners. Low-level attack in broad daylight 300 m into occupied territory, then the flight home through alerted defenses. Group Captain Percy Pickard took command, assembling crews from 140 Wing, experienced men who'd flown Oslo, Berlin, and targets even more optimistic than those. The planning consumed 4 days. Photographic reconnaissance revealed the prison's layout in detail. Outer walls 2 feet thick, guard barracks adjacent to the main building, German quarters that needed destroying, whilst French sections remained theoretically intact. The bombing would occur at rooftop height, perhaps 50 feet, which meant the blast from your own weapons could shatter your aircraft if timing wavered. 19 Mosquitos lifted from RAF Hunden on the morning of 18th of February. The execution date had been moved forward. The formation flew wavetop across the channel, navigation by stopwatch and compass, arriving over AMO at precisely 12:03. Picard's aircraft led the first wave, 6 Mosquitos climbing to 150 feet for their attack runs. The bombs struck perfectly, blowing sections of the outer wall into rubble, breaching the eastern wall near the condemned cells. The second wave targeted the guard quarters, collapsing buildings and creating chaos. The third wave remained in reserve, circling, but wasn't needed. Intelligence reports later confirmed 258 prisoners escaped in the confusion, including most of those scheduled for execution, but the successful bombing was merely the first survival problem. The attack had occurred at midday, with German radar stations fully alert. As the Mosquitos regrouped for the return flight, Luftwaffe controllers scrambled every available fighter from airfields between Amy and the coast. The British aircraft faced 40 minutes of exposure before reaching the channel, flying over countryside where every road held Wehrmacht units with radio communication. Pickard's Mosquito never made it home. 2 Focke-Wulf 190s caught him near Bet, their guns finding the aircraft before evasion was possible. Pickard and his navigator died instantly. 2 other Mosquitos felled the fighters in those brutal minutes after the attack, crews paying the price for flying straight and level during bomb runs. The remaining 16 aircraft survived largely because of modifications Banks had now standardized. Squadron leader Ian Critty, leading the second wave, encountered 4 FW-190s climbing to intercept near Aberville. His modified Merlin gave him the 10 miles per hour that transformed potential combat into a foot race he could win. The German pilots fired optimistically at maximum range, their 20mm rounds falling away behind Critt's tail plane as the gap expanded. Flight Lieutenant Bobby Yardale faced a more sustained pursuit. A 109 G6 bounced him from clouds south of Among, the German pilot executing a textbook attack that should have ended with Yardale's Mosquito scattering across a French field. A Yardale slammed the throttles forward, feeling the engine note change as boost pressure climbed into Banks's modified range. The 109 pilot stayed with him initially. The Gustav variant was formidable in level flight, capable of 390 miles per hour at low altitude, but capable of and sustained are different concepts. The Messerschmitt Daimler-Benz engine was rated for specific power settings, and like the Merlin, exceeding them invited mechanical trauma. For 3 minutes, the two aircraft screamed across Picard at full power. The 109 holding position about 600 yards behind Yardale's tail. Close enough to worry, too far to kill. Then slowly, incrementally, the gap began opening. Not dramatically. This wasn't the decisive acceleration Channer had experienced at altitude. At low level, air density robbed both aircraft of performance. But Yardale's Mosquito maintained 405 miles per hour, where the 109 could sustain only 395. 10 miles per hour, compounding across 3 minutes, became half a mile of separation. The German pilot fired a final burst at impossible range and broke away, probably cursing his fuel state. 12 of the returning Mosquitos carried Banks's modifications. All 12 made it home. The 4 losses included Pickard's unmodified aircraft and 3 others flying standard specifications. The sample size was small, the statistics not definitive, but the crews drew their own conclusions. By March, Banks was receiving requests from squadrons he'd never heard of. Engineering officers turning blind eyes to modifications they couldn't officially acknowledge. Hermann Göring's rage was becoming legendary even by his theatrical standards. During a meeting at Carenhall on 8th of March 1944, he interrupted a Luftwaffe technical briefing to demand why German fighters couldn't catch wooden British furniture. The Reichsmarshal's frustration was understandable. Mosquitos were appearing over Berlin in daylight, photographing the Chancellery, whilst Bf 109 scrambled uselessly below. The humiliation was tactical, political, and deeply personal. Göring had promised Hitler air superiority. Instead, plywood bombers mocked that promise at 400 miles per hour. The Luftwaffe's response revealed desperation disguised as innovation. Messerschmitt and Focke-Wulf received urgent directives to extract more speed from existing airframes. Engineers knew the problem's dimensions. The Mosquito at altitude with competent crew represented a performance envelope their fighters couldn't quite reach in sustained chase. Close. Maddeningly close. But aviation doesn't award points for proximity. Messerschmitt's solution was the 109 G10, introducing a Daimler-Benz DB605D engine with improved supercharging and emergency boost, raising output to 2,000 horsepower. On paper, impressive. In practice, the modifications added weight that partially negated the power increase. The G10 could touch 426 miles per hour at optimal altitude, but only briefly. And only if the pilot accepted engine life, measured in hours rather than days. German maintenance logistics couldn't sustain such abuse across operational squadrons. Focke-Wulf pursued the TR-152. Kurt Tank's obsessive refinement of the Wonder 90 design. Longer wings, pressurized cockpit. Junkers Jumo 213 engine producing 250 horsepower with MW50 methanol water injection. The prototypes achieved remarkable performance. 472 miles per hour at 41,000-foot altitude capability that should have dominated Mosquito operations. But development consumed time Germany didn't possess. The first TR-152s reached operational units in January 1945. Too late and too few to affect strategic outcomes. The Luftwaffe also attempted mimicking Banks's approach, unauthorized boost increases on existing engines. Several fighter staff experimented with adjusting boost controls on DB605 and BMW 801 power plants, seeking the margin British pilots apparently enjoyed. The results were catastrophic. German engines lacked the Merlin's robust construction and suffered from increasingly poor manufacturing quality as Allied bombing disrupted production. Bearings failed, pistons cracked, connecting rods punched through crankcase walls, and Me-109 disintegrating over its own airfield because the pilot demanded too much was a training film for what not to attempt. The fundamental problem wasn't merely engineering. It was industrial capacity under siege. Rolls-Royce's Derby and Crewe factories operated with consistent material quality, skilled labor pools, and uninterrupted supply chains. German aero engine production by 1944 involved dispersed facilities. Slave labor of varying skill and materials substituted when proper alloys became unavailable. Tolerances suffered. Quality control became theoretical. An engine that measured correctly on paper might hide flaws that emerged only under stress. Oberst Adolf Galland, General de Jagdflieger, understood this reality with bitter clarity. In an April 1944 memorandum to Goering, Galland noted that even when German fighters achieved successful interceptions of Mosquitos, the bombers often escaped through sustained high-speed flight that our aircraft cannot match without risking mechanical failure. He requested permission to withdraw fighters from less critical areas to concentrate overwhelming numbers against Mosquito routes, accepting losses elsewhere to guarantee kills against the fast bombers. Goering rejected the proposal. The Reichsmarschall remained convinced that technical solutions existed, that German engineering superiority, an article of Nazi faith, would produce aircraft to humble British plywood. He diverted resources toward jet fighter development, the Mi-262 promising speed that would render the Mosquito obsolete. The jets did eventually fly, and they were indeed fast enough, but they arrived in handfuls when hundreds were needed, piloted by hastily trained crews, burning fuel Germany couldn't spare. Meanwhile, Mosquito operations intensified. The fast bombers struck targets in broad daylight that heavy bombers attacked only under darkness. Ball-bearing plants at Schweinfurt, V-weapon sites along the French coast, Gestapo headquarters in Copenhagen. The psychological impact exceeded the physical damage. German civilians watching Mosquitoes streak overhead untouched by flak or fighters understood their vaunted Luftwaffe had lost control of the sky. Some Luftwaffe pilots developed grudging respect for their elusive opponents. Hauptmann Heinzgau, a veteran with 33 victories, wrote in his diary after a failed Mosquito interception, "The Tommy flew like the devil was behind him." Or perhaps the devil was inside his engines. Note didn't know about Banks, about modified boost controls and enriched fuel mixtures, but he recognized that something beyond the design office gave those wooden bombers their edge. By autumn 1944, Banks's workshop at Maham had become something between legend and logistical necessity. Crews arriving from other stations brought bottles of whiskey and engineering problems, hoping the sergeant with the magic touch might examine their Merlin. Banks obliged when time permitted, but the demand outstripped what one man could physically achieve. The solution emerged organically. He began training others, passing knowledge to fitters who demonstrated both technical aptitude and appropriate discretion. The network expanded carefully. Banks identified candidates through recommendation, preferring mechanics who'd worked at Rolls-Royce facilities or demonstrated unusual initiative. He'd invite them to observe an engine modification, explaining the theory whilst his hands performed the practice, the boost control adjustment, the fuel jet replacement, the magneto timing advance. Each procedure was demonstrated twice. Then the student attempted it under supervision. Banks rejected anyone who couldn't articulate why each modification worked, not just how to execute it. Understanding prevented catastrophic mistakes. Flight Sergeant Thomas Yardley became Banks's most accomplished student. Yardley had spent 3 years at Rolls-Royce's Hillington factory near Glasgow before joining the RAF, and he possessed an intuitive grasp of thermodynamics that Banks recognized immediately. By November 1944, Yardley was modifying engines at RAF Koningsby, serving Lancaster squadrons that were beginning to receive Merlin-powered variants. The modifications transferred successfully to the heavy bombers, though the performance gains were less dramatic. A Lancaster couldn't outrun fighters regardless of engine tweaks. But the extra power improved climb rates and high-altitude ceiling, making them marginally harder targets. Corporal James Dennison established another node at RAF Whiteton in Cambridge, focusing exclusively on Mosquito squadrons. Dennison was younger than Banks, only 23, but he'd absorbed the lessons thoroughly. His contribution was refining the fuel mixture adjustment for different operational profiles. Mosquitoes flying low-level anti-shipping strikes needed different mixture settings than those conducting high-altitude reconnaissance. Dennis worked out the variations, creating what amounted to MIS-specific engine configurations. The unofficial network operated through careful information control. Modifications were never discussed over telephone lines or mentioned in official correspondence. Knowledge passed face-to-face, mechanic to mechanic, usually during station visits that officially concerned routine maintenance matters. Squadron engineering officers developed plausible deniability. They knew something was happening to engine performance, but the paperwork showed only standard overhauls and adjustments. If questioned by higher authority, they could honestly claim ignorance of specifics. This arrangement suited everyone except the regulations. Air Ministry engineering directives still required all modifications to receive formal approval, testing, and documentation. Banks's network violated that structure entirely, operating as a shadow system, optimizing aircraft through channels bureaucracy didn't acknowledge. The situation was sustainable only because results overwhelmed objections. Mosquito squadrons with access to modified engines showed consistently better operational statistics, higher sortie completion rates, lower combat losses, more successful target engagements. Yet, the modifications carried genuine risks that Banks never downplayed. Engines running at elevated boost pressures accumulated fatigue faster than standard power plants. Components that might normally survive 200 hours between overhauls sometimes required replacement at 150 hours. Piston crown erosion occurred more frequently. Exhaust valves showed increased wear. The performance came with a maintenance bill that someone had to pay. More seriously, catastrophic failures did occur. In December 1944, a Mosquito taking off from B suffered a connecting rod failure in the port engine at 400 feet. The rod punched through the crankcase. Oil sprayed across the hot exhaust manifold and fire erupted immediately. The crew nursed the aircraft around the circuit on the remaining engine and landed successfully. But the fire destroyed the wing before ground crews could extinguish it. The post-ac investigation revealed the failed engine had been modified 3 weeks earlier. Banks examined the wreckage personally. The failed connecting rod showed fatigue cracking consistent with excessive loading over multiple flights. The engine's service records indicated it had accumulated 178 hours since overhaul within normal limits. But Banks had specified that modified engines should be pulled at 150 hours regardless of apparent condition. The responsible fitter had missed the deadline by 28 hours. Those hours had cost an engine and nearly killed 2 men. The incident prompted Banks to formalize his informal network slightly. He created a simple tracking system, a small notebook where each modified engine received a line entry with serial number, modification date, and hour limit. Copies went to his trained fitters with explicit instructions. Pull the engine at the limit regardless of how healthy it appeared. The extra conservatism reduced the failure rate to near zero over subsequent months, though it increased maintenance workload. Station commanders faced a peculiar dilemma. They couldn't officially authorize modifications that violated Air Ministry protocols, but they couldn't afford to lose the performance advantage those modifications provided. The solution was studied ignorance. Engineering officers received verbal guidance to ensure engines are maintained to optimal performance standards, phrasing vague enough to mean anything or nothing depending on interpretation. The cost became impossible to ignore on 14th of January, 1945. Flight Lieutenant David Wilson and his navigator were 40 minutes into a reconnaissance sortie over Kiel when the starboard Merlin's temperature gauge surged past safe limits. Wilson throttled back immediately, but the damage was progressing. Oil pressure dropping, metal temperatures climbing despite reduced power. He turned for home, nursing the failing engine whilst the Port Merlin carried disproportionate load. They nearly made it. 8 miles from the English coast, the starboard engine seized completely, the propeller windmilling uselessly. Wilson ditched in the North Sea. Air Sea Rescue found them 90 minutes later, hypothermic, but alive. The engine stripped down revealed a failure cascade that began with a cracked exhaust valve. The valve had been running hot, a consequence of elevated cylinder temperatures from sustained high boost operation, and microscopic cracks had propagated through the valve face over multiple sorties. During the fatal flight, a piece of the valve face had broken away, dropped into the cylinder, and hammered the piston crown into fragments. Those fragments destroyed the cylinder wall, contaminated the oil with metal particles, and the abrasive slurry killed the bearings within minutes. Banks read the investigation report with the expression of someone watching a predicted disaster finally arrive. He'd known from the beginning that sustained high-power operations stressed components beyond their design life. The question had always been whether the tactical advantage justified the mechanical price. Wilson's near death provided an uncomfortable answer. The mathematics of acceptable loss were brutal. Between June 1944 and March 1945, Mosquitos with modified engines flew approximately 3,400 operational sorties. Combat losses totaled 11 aircraft, a loss rate of 0.32%. Standard specification Mosquitos flying comparable missions lost 47 aircraft from 6 to 800 sorties, 0.69%. The modified aircraft were statistically twice as likely to return. But those same modified engines suffered 23 mechanical failures severe enough to force emergency landings or abandonments. 3 crews died in crashes directly attributable to engine failure. Another 7 suffered injuries. The moral arithmetic troubled Banks more than he admitted. Each modification he approved might save a crew from German fighters, but simultaneously place them at risk from their own power plants. The decision wasn't his alone. Pilots requested the modifications, understanding the trade-offs, but Banks felt the weight of consequences. When an engine failed, he knew his hands had adjusted those boost controls, selected that fuel jet, advanced that magneto timing. Squadron engineering officers faced similar calculations. They could maintain engines to PCM standards, accepting the performance penalty, or they could push boundaries and accept occasional catastrophic failures. Most chose the latter, reasoning that combat killed with far greater efficiency than mechanical unreliability. A crew shot down over Germany faced death or years in prison camps. A crew forced to ditch from engine failure usually survived if rescue services responded quickly. The North Sea was brutal, but it wasn't the Gestapo. Rolls-Royce remained officially oblivious to the widespread modifications, but company engineers weren't stupid. Field service representatives visiting RAF stations noticed engines returned for overhaul, showing where patterns inconsistent with rated operating conditions. Questions were asked, carefully vague answers provided. The representatives reported their suspicions to Derby, where senior management faced an uncomfortable reality. Their engines were being operated beyond specification, apparently successfully, and complaining might force the RAF to stop, reducing the Mosquito's effectiveness. Some Rolls-Royce engineers were privately fascinated. The company had been conservative with the Merlin's ratings, prioritizing reliability over maximum performance, but they'd always suspected additional margin existed. Banks' modifications were essentially an unsanctioned field test program, providing data that PCM testing would never generate. Engines run to destruction under combat conditions. Thousands of hours of high-stress operation, all documented in maintenance logs. The human cost extended beyond crashed crews. Ground crew working on modified engines operated under constant pressure. They knew each decision. Approving an engine for flight, delaying an overhaul by 10 hours, accepting a marginal temperature reading, carried life or death consequences. Flight Sergeant Yardley developed an ulcer by early 1945, the stress of responsibility manifesting physically. Several fitters requested transfers to non-operational units unable to sustain the psychological burden. Banks himself showed the strain. Photographs from late 1944 reveal a man who'd aged substantially in 2 years. The confident mechanic who'd first modified DZ-414 had become someone who understood that innovation killed as well as saved. He still believed the modifications were necessary. The combat statistics supported that conclusion, but necessity didn't eliminate guilt when things went wrong. The question of whether to continue became moot in February 1945 when Rolls-Royce's chief engineer arrived at Marham unannounced. Ernest Hives didn't announce his visit because he wanted to see reality, not a sanitized version prepared for management inspection. The managing director of Rolls-Royce's Aero Engine Division arrived at RAF Maham on 12th of February, 1945. Driving himself in a staff car borrowed from the Air Ministry, he found Banks in Workshop 3, elbow deep in a Merlin that had accumulated 147 hours since its last modification. Hives watched silently for 10 minutes before speaking. "Show me what you're doing, Sergeant." "All of it." The conversation that followed lasted 3 hours. Banks explained the boost control modifications, demonstrated the fuel jet replacements, walked Hives through his decision matrix for selecting which engines received treatment. He didn't apologize or justify. He simply presented the technical reality and the combat results. Hives asked precise questions about detonation margins, bearing loads, and thermal stresses. This wasn't an interrogation. It was two engineers discussing problems most people couldn't comprehend. Hives had brought service records for 200 Merlin engines randomly selected from operational squadrons. He spread them across a workbench, sorting modified from standard power plants based on wear patterns. Visible in the documentation, the modified engines showed measurably higher component wear, exactly as Banks had predicted, but failure rates remained within acceptable bounds, provided maintenance discipline stayed rigorous. What surprised Hives was the consistency. Banks' modifications weren't random tinkering. They represented a coherent engineering approach applied systematically. The Rolls-Royce director asked about failures. Banks provided his notebook, the simple log tracking every modified engine, 23 mechanical failures across 3,400 sorties, a failure rate of 0.68%. Hives compared this to the standard Merlin's operational failure rate of 0.31%. The modified engines failed twice as often, but aircraft equipped with them survived combat at twice the rate. The net effect was fewer dead air crew. From a purely utilitarian perspective, Banks's modifications saved lives. Hives's response surprised everyone present. Rather than ordering the modifications stopped, he thanked Banks for identifying performance margins Rolls-Royce had been too conservative to exploit. The company had indeed built substantial safety factors into the Merlin's ratings, and combat operations had revealed those margins were larger than necessary. Banks hadn't discovered anything Rolls-Royce engineers didn't theoretically know. He'd simply been willing to act on it without waiting for committee approval. Within weeks, Rolls-Royce issued Technical Service Bulletin 184 dated 7th of March, 1945. The document authorized increased boost pressures for Merlin engines in specific applications, essentially codifying Banks's modifications with official sanction. The bulletin specified conditions. Engines must be fresh from overhaul, operating on verified 100-octane fuel with mandatory inspections at 150-hour intervals. The enriched fuel mixture became standard for high-power settings. Magneto timing remained unchanged. Rolls-Royce judged the crankshaft stress increase excessive for general application, though they didn't prohibit it. The bulletin transformed Banks's gray market modifications into approved procedure overnight. What had been technically illegal became officially sanctioned, retroactively justifying 2 years of unauthorized engineering. More significantly, it vindicated Banks's technical judgment. Rolls-Royce wasn't simply tolerating his work. They were adopting it. The impact extended beyond the Mosquito. Merlin engines powering late-model Spitfires and Mustangs received similar modifications, improving high-altitude performance against German jets. The Merlin 100 series engines developed for post-war applications incorporated lessons learned from wartime field modifications, including improved detonation resistance and higher sustainable boost pressures. Banks's fingerprints were all over the Merlin's final evolution, though his name appeared nowhere in official development records. Recognition arrived in peculiar forms. Banks received promotion to warrant officer in April 1945, unusual for someone without aircrew qualification. The citation mentioned exceptional technical contributions to operational effectiveness, bureaucratic language that concealed the actual achievement. Several pilots whose lives had been saved by modified engines wrote personal letters, though most simply shook his hand during station visits and said nothing more. The best thank you was coming home alive. Rolls-Royce offered Banks a position at Derby after the war ended, a role in experimental engine development where his willingness to push boundaries would be asset rather than liability. He accepted, leaving the RAF in September 1945 with a service record that described him as competent and reliable, damning with faint praise that entirely missed the point. The final operational tally was recorded in June 1945 after Germany's surrender. Mosquitos equipped with modified engines had flown 8 200 sorties in the war's final year, losing 27 aircraft to all causes, 0.33%. Standard Mosquitos in the same period, for 1,100 sorties, 31 losses, 0.76%. The statistical evidence was overwhelming. Banks's modifications had cut combat losses by more than half, saving roughly 200 aircrew lives through simple mechanical adjustments that cost nothing but careful attention. The Air Ministry never officially acknowledged the modification's role in Mosquito's success. Official histories credited the aircraft's inherent design excellence, which was true, but incomplete. The Mosquito was brilliant, but Banks made it better. Roderick Banks died in 1992, age 76, in suburban Derby, where he'd spent 47 years refining engines for Rolls-Royce. His obituary in the Derby Telegraph mentioned a distinguished career in aerospace engineering, but said nothing about Mosquitos or wartime modifications. The story might have disappeared entirely except for a chance conversation at a 1995 Mosquito reunion where 3 veterans independently mentioned Banks's engines, and a historian finally asked what that meant. The full account emerged gradually pieced together from maintenance logs, squadron records, and interviews with surviving ground crew. What became clear was that Banks had achieved something rare: meaningful tactical innovation from below. A sergeant identifying performance margins that engineers and officers had missed or feared to exploit. Military organizations theoretically encourage initiative, but in practice they're structured to prevent exactly what Banks did: unauthorized modification of expensive equipment based on individual judgment. His success revealed uncomfortable truths about engineering conservatism. Rolls-Royce's safety margins, whilst prudent for general application, were excessive for engines maintained to the highest standards and operated by skilled crews. Banks recognized that safe for all conditions wasn't the same as optimal for specific conditions. The Merlin could sustain higher performance if you controlled the variables: perfect maintenance, quality fuel, rigorous monitoring. The company's blanket restrictions prevented accessing performance that was genuinely available. This insight has modern relevance. Contemporary aircraft engines operate under similarly conservative ratings, manufacturers protecting themselves from liability and variable operational conditions. Military and commercial operators routinely discover that engines can deliver more than certified specifications suggest. But exploiting that margin requires exactly what Banks demonstrated: deep technical knowledge, obsessive quality control, and willingness to accept accelerated wear in exchange for performance. The modifications also illustrated the difference between engineering in peacetime and war. PCM prioritizes longevity, cost-effectiveness, and safety margins that accommodate imperfect maintenance. War prioritizes survival, accepting reduced component life if it keeps crews alive today, regardless of tomorrow's maintenance bills. Banks understood that an engine that survived 150 hours instead of 200 was acceptable if those 150 hours prevented a crew from dying in Mine 47. Modern military aviation still grapples with this tension. Fourth and fifth generation fighters have official performance limits and unofficial combat limits that pilots use when survival demands it. The F-15's engine, for example, has standard thrust ratings and emergency ratings that shorten engine life but provide crucial performance. Banks pioneered this doctrine for his era, establishing that survival justifies accelerated wear. The Mosquito's post-war reputation benefited enormously from modifications it carried during the conflict. Performance figures cited in histories often reflected Banks' modified aircraft, not standard specifications. The Mosquito became legendary partly because Banks made it faster than de Havilland's original design. This creates historical irony. The aircraft's iconic speed resulted from unauthorized field modifications that technically violated every regulation governing aircraft maintenance. Engineering education occasionally examines Banks's work as a case study in practical problem-solving versus institutional procedure. His modifications demonstrated technically sound reasoning applied outside official channels, raising questions about when rules should be followed and when they should be challenged. There's no comfortable answer. Banks was right. His modifications saved lives. But if he'd been wrong, if engines had failed catastrophically at higher rates, he'd have been court-martialed for recklessness. The broader lesson concerns innovation's source. Transformative improvements often come from unexpected places, not design offices or research departments, but workshops where people directly confronting problems develop solutions unconstrained by institutional thinking. Banks wasn't smarter than Rolls-Royce's engineers. He was differently positioned, facing different incentives, willing to accept risks that company engineers couldn't. His workshop at Maham was demolished in 1962 during station modernization. Nothing marks the location where Banks modified DZ-414 or trained the fitters who spread his techniques across squadrons. The Mosquito that carried his modifications to Operation Jericho survived the war and was scrapped in 1947. Its historically significant engines melted down for aluminium value. Physical evidence disappeared, leaving only documentation and fading memories. Yet Banks's influence persists in ways he never witnessed. Modern engine development incorporates field feedback mechanisms specifically designed to capture the kind of insights he generated. Operators reporting performance margins. Engineers investigating unauthorized modifications rather than simply prohibiting them. Rolls-Royce's successor companies maintained formal channels for field service representatives to report unusual but successful operational practices, institutionalizing what banks did informally. The Mosquito's legend endures because it succeeded spectacularly at missions everyone said were impossible. It flew to Berlin and back,